everyone. In this video, we're going to talk about how to use Fleury's algorithm to find the Euler paths and Euler circuits in a graph. So take 3 deep breaths and let's make this math easy. All right, so the goal of Fleury's algorithm is to find an Euler path or an Euler circuit in a graph. So just as a reminder, an Euler path is a path that uses every edge exactly once. So for example, in this first graph, I could start at B, go to A, C, D, B, C, and because every edge was used exactly once, that makes that path an Euler path. And then an Euler circuit is basically the same thing, except that you have to begin and end at the same point. So let's say I started at vertex A, I could go A to D, to E, to C, to F, to E, to A, to C, to B, to A. And because I used every edge exactly once, and I ended up back where I started, that means that that's an Euler circuit. So the steps for Fleury's algorithm is first you use the Euler circuit and path theorem to verify that it's even possible to find an Euler circuit or path. So you find the degrees of all the vertices, and if they're all even, then you should be able to find an Euler circuit. And if there's 2 odd ones, but all of the rest of them are even, then you should be able to find an Euler path. Then, if you determine that it is possible to find an Euler circuit, you can choose any vertex as your starting vertex. But if it's an Euler path, like if 2 of them are odd, then you're going to choose one of the vertices that has an odd degree and make that one your starting vertex. Then you choose any edge that's attached to the current vertex. And you travel along that edge as long as deleting that edge won't make the graph a disconnected graph. So that's kind of the key part of Fleury's algorithm, is you just choose edges that will not make the graph disconnected. So you choose one of those edges, add the edge to your circuit, and you delete that from the graph. And then you continue doing that over and over and over until all of the edges in the graph are deleted and you've completed your circuit. So for example, on this one, if we were doing Fleury's algorithm, the first thing we would do is we'd check the degree of all of the vertices to see if they're even or odd, because that's going to determine whether a path or a circuit is possible. So I'm going through and calculating the degree of all of these vertices, and it looks like they're all even. So that means that it's possible to do a circuit. And with a circuit, it doesn't matter which vertex you use as your starting point. So I'm just going to go ahead and use this vertex here as my starting point. And I'm going to actually record my circuit as I go, because on your assignments, you're going to have to write out what the sequence of vertices is. So I'll do that in my example. So I say, okay, well, this is my starting vertex, and I can choose any of the edges that leave that vertex as long as deleting the edge would not create a disconnected graph. So in this case, neither one of them would, and so I can just choose whichever one I want to. So I'm going to choose this one, which means I go to vertex B. And then from vertex B, I'm going to choose another edge that will not disconnect it. So let's say I choose this edge and I go to D. Then from D, I'm going to choose an edge, and none of those edges would disconnect the graph. So maybe I'll go over to U. And there's lots of different choices you could do. So that it's not like there's just one correct circuit. And this is just the choice that I made, but if you made a different choice, you might end up with a different circuit, but you would still get an Eulerian circuit. So now that I'm at vertex U, I'm going to look at all of the edges that leave, and it looks like none of them would disconnect the graph. So I'll go up to W. And again, I just chose that one. I could have chosen to go to E or to V if I wanted to. And from W, I only have one choice of where I can go. So I'll choose this edge and delete it. So all of these edges that I'm highlighting, that means I'm deleting them. So from V, there's only one edge I can choose, and that's the one that takes me back to U. And then I can go from U to E. Now, if I were to go back to C, that would make the graph disconnected because I would still have these other edges I haven't used yet. So I can't go back to A, but I can go to B or to D. So I'm going to choose to go to D. And then from D, I'm going to go to C. And then from C, I'm going to go to B. And then from B, I'm going to go to E. And then I'm going to go from E to C. And so this is the circuit that I created with Fleury's algorithm. And this sequence of vertices describes the path that I followed to complete the circuit. Now, this is not the only circuit that's possible because it just depended on which edges I chose to delete. So if you were to do this same problem, you might end up with a different circuit. But Fleury's algorithm will always give you some Eulerian circuit on the graph, which is kind of the goal of Fleury's algorithm. So let's do another example. So on this one, let's go ahead and calculate out the degree of each vertex. So vertex 0 has degree 4 because there's 4 edges leaving it. Vertex 1 has degree 5. Vertex 2 has degree 4. Vertex 3 has degree 4. Vertex 4 has degree 4, 5 has degree 4, and vertex 6 has degree 5. So when I look at this graph, I know automatically that it's not possible to do an Eulerian circuit because the path and circuit theorem tells me that they all have to have an even degree. And in this case, we have 2 vertices that have an odd degree. But because there's only 2, that means that it is possible to do an Eulerian path because an Euler path can start and end on different vertices. So essentially these 2 odd degree vertices are going to be my starting and ending points. So on Fleury's algorithm with this one, I either have to choose vertex 1 or vertex 6 as my starting point. So I'm just going to go ahead and choose vertex 1 as my starting point, and I'm going to choose any edge that will not disconnect the graph. So in this case, it doesn't matter which edge I choose, so I'm going to go back to vertex 0 as my next one. Then maybe I'll go to vertex 3 because that doesn't disconnect the graph. Then I'll go to vertex 2, and at this point, I can't choose this edge right here because if I were to choose that edge, it wouldn't include all of the rest of the edges in the graph and it would disconnect the graph. And so I can't choose that edge, but I can choose any of the other ones. So I'm going to choose this one and go to vertex 5. Then maybe I'll go over to vertex 4. And then I'll go to vertex 3 and maybe go over to 6. So maybe I'll go to vertex 5. And then at this point, I only have one option to go back to 1. So I'll go back to vertex 1. And then maybe I'll go to vertex 2, and then I'll go to vertex 6, and then maybe I'll go up to 0, and then go to 4, and then go up to 1, and then go back down to 6. And so this sequence of vertices that I've drawn here is the path that starts at vertex 1 and ends at vertex 6. And so notice that I chose an odd degree vertex as my starting point, and this algorithm automatically gave me an Euler path that ended at the other odd vertex. So that's how you would use Fleury's algorithm to find an Euler path. So Euler circuits happen when all of the degrees of the vertices are even, and Euler paths can either happen when they're all even, because a circuit is a path, it's just a special type of path, or it can also happen if you have two odd degree vertices, but those two vertices will basically just be your starting and ending points. So if you have any questions, let me know, and I hope you guys have a good day.